In this video, I'm going to continue discussing quantum scattering theory. And so this will be one of the methods we can use for finding that scattering factor that I discussed in the previous video. And this method is called the partial wave analysis. And so recall from quite a while ago in a different video, the hydrogen atom, we could separate the wave function to look like this. So we have the radial part here, and then this is the spherical harmonics right here. So the radial part was dependent on the R here, where the spherical harmonics is dependent on the theta and phi right here. And so if we are looking at the radial part of the equation, we can make this substitution. So this u of r here is equal to r times this big R of r right here. And so we end up getting this for our Schrodinger equation. And so this part right here, if you recall, was the centrifugal force part of it. In particular, we are concerned with this part here, this L times L plus 1 over R squared, where the L's, remember, are the angular momentum quantum numbers. So at very large R, the potential and the centrifugal force will become negligible. And so we end up with this right here, and we make the substitution with this K right here for this energy term, and so we end up with this K squared here, and we ended up with this right here, which had a general solution for our u of r being this right here. So this linear combination of these imaginary exponentials right here. Since this is the incoming wave, and we are interested in the outgoing or the scattered wave, we just set d equal to 0. And since our u of r was equal to this, we get u of r over r, and so we get that for very large r, our radial equation is equal to this e to the ikr over r right here. So we have to think about three different regions. So remember, we have this sort of scattering center right here, which has this potential around it, and so we're looking at sort of a wave coming in here, and so it's going to run into this potential, and then some stuff is going to happen, and then we will have sort of a well, we'll have a spherical wave, so that will have these different crests and troughs sort of going outward from the center here, so going outward in all directions. And so we have to think about sort of, or we don't have to, this is kind of the way we think about it. It's sort of the way to make this easier for us. So we have to think about the region inside the potential, so that's where the potential is not equal to 0, and therefore the centrifugal term will also not be equal to 0. There will be an intermediate region where the potential is, and this should probably actually be roughly equal to 0. So it's close enough that we can just call it 0, but we will still have this centrifugal term that will not be equal to 0. Then we will have the distant region when r is large, and so we can think of, or the potential will be 0, and we can think of the centrifugal term here being 0. So it's in this region here, this distant region, that we need the wave function to be a superposition of the incoming plane wave and the outgoing spherical wave. And so it will look like this. So we have this e to the ikz here as our incoming wave, then this e to the ikr right here as our outgoing wave, and it's multiplied by this scattering factor. And so we have to find what this scattering factor is. And so here are those regions right here. So everything's sort of outside this circle. So in the white out here is the sort of large R where our potential is 0 and our centrifugal term here is 0. Then in the intermediate range, we have our potential being roughly equal to 0, but our centrifugal term is not 0. Then inside the potential in this purple area here, our potential and our centrifugal terms are not 0. And so we will first look at this intermediate region. And so again, the potential is roughly 0 and our centrifugal term is not equal to 0. And so we will end up with this as our Schrodinger equation right here. And so the general solution for this are the spherical Hankel functions that look like this. So we have the spherical Hankel function of the first kind and the second kind here, which are just the sort of complex conjugates of each other right here, where this n sub L and this j sub L here are the spherical Bessel functions. And so we have here this is the first kind of spherical Bessel function. This is the second kind, which is often called the Neumann functions right here. So this is sort of the general form of it right here, and right here for both of those. And so we see that these are going to be sort of sine over x and negative cosine over x terms here, where we are taking these derivatives here. And so the derivatives of cosine and sine are just sort of changing back and forth between each other. And we have this 1 over x part here that is to these powers of L here. And so those will increase in power. So we'll have 1 over x, then 1 over x squared, and so on. So we can actually see that right here with these ones. So this will have this sine over x squared and then this minus cosine over x and so forth. And so we keep increasing these powers of x in the denominator. But then because we have these trigonometric functions here for these e to the ix and e to the negative ix, we can put these Hankel functions of the first and second kind as being analogous to this e to the ikr and e to the negative ikr. And so we end up with these right here, where this and this are the general forms of it. But we see that the first version of these, or the sort of h sub 0 on these, have this e to the ix over x and this e to the negative ix over x terms right here, where after that these keep getting higher and higher orders of magnitude in the denominator, which will be important for us to keep in mind here. And so for the outgoing wave, we will use the radial equation, the Hankel function of the first kind here, because like I said, these ones keep getting higher and higher order here, and we will see that as the r gets large, that those ones just kind of go towards 0. Since we're assuming the potential is spherically symmetric, which is a decent assumption to make, like if we're talking about just an atom and we're talking about the nucleus of the atom that's going to have a spherical symmetrical potential. It means it doesn't depend on the phi, and so the quantum number m is equal to 0, and so our spherical harmonics will always use the m equal 0 on these, though the L, well, it'll be a linear combination of the L's here. So we have the spherical harmonics being this right here, which is this term multiplied by these Legendre polynomials. And in fact, I believe those are actually the associated Legendre polynomials. And by the way, if these sort of polynomials, these associated Legendre polynomials, and these Bessel functions and Hankel functions, if you're not familiar with all this stuff, I would recommend checking out my playlist on the special functions of differential equations, where I talk about these kinds of things in a lot more detail. And I would definitely check out the solutions to the Schrodinger equation for the hydrogen atom and the spherical potential and stuff like that earlier on in this quantum mechanics playlist. But like I said, yeah, these are the associated Legendre polynomials, and therefore we have this as our wave function. So remember, this e to the I k z here is our incoming wave, and then this is our scattered wave right here. So yeah, the first term is in the bracket is the incoming wave. This is the second is the superposition of the outgoing spherical wave. So it's a superposition of the of the different angular momentum for those waves right there. So we have this for our spherical harmonics right here. We can then redefine the expansion coefficients with m equals 0. So we make this substitution right here where this a sub L is called the partial wave amplitude. And we'll actually see in the next video that that is related to a phase change in the outgoing waves. And so you can kind of think about that as being like the sort of phase change going on as these different waves with different angular momenta sort of spread out in a sphere from the central potential. And so we end up, after doing some math, we end up getting to this that I have here in the blue, which is, remember, this is the wave function for the intermediate zone of that potential, where our where we can say that our potential is roughly 0, but our centrifugal term is not 0. All right, so we can look at very large r's. So this is sort of, so again, we look up here, the blue zone is our intermediate region. We're now out here in this region outside of that, so at very large R. And so we can say that our potential and our centrifugal term are both 0. This is often called the radiation zone right here. So our Hankel function of the first kind, as I said, will converge on this because all the higher order terms will go to 0, and so we end up having this right here for our Hankel functions of the different L's, and so the different L's will have this be different right there, but this part of it will be the same for all of them because those higher order terms where we have higher kr squared, kr cubed, and so forth will quickly go to 0. And so this is spherically symmetric, and so we can put this into our solution from the intermediate region. So we're putting it into this right here. So this Hankel function right here, we're putting this in for that right here. So we do that, we cross out the k's, and we end up with this right here. But this is not dependent on the L, and so we can pull this out of the summation, so we end up with this. And so this is our incoming wave, this is our outgoing wave, and so this part here, this summation, must be our scattering factor f of theta right there. And so this is our scattering factor right there. Which means that the differential cross section, which remember was the square of that scattering factor, will be this right here. But we can do some simplifications because our associated Legendre polynomials are orthogonal between 1 and -1 here. So these blue ones here with the L prime have to be equal to the to these P sub L right here. And so we end up with this delta function right here. So that's just saying that if these are not equal, then it's 0, and if they are equal, then it's 1. And so we also have this this L and this L have to be the same in these in this part of the differential cross section right there, so we can just put this as squared. We multiply it by this, which we get from those associated Legendre polynomials, so we end up with just the 2L plus 1, which leaves us with this right here. So it's just the summation over L of this 2L plus 1 times the square of our partial wave amplitude there. So these will have to be the same too, because the L's have to be the same on those. So we end up with this for our d theta. So remember that the d theta is equal to this d sigma over d omega. So our d sigma over d omega will be equal to this summation here. We can sort of multiply both sides by this d omega. We get this. Then we take the integral of both sides, which will turn this d sigma just into sigma, and we take the integral of this side right here. And what we will end up with is the total cross section, which is what we have right here. So because we're integrating over phi, we will end up with this 4 pi right here. And so we then need to solve so this was, again, this was looking at this solution for the very large R, where we just put the spherical Hankel function here into our what we got here for the wave function for the intermediate region. So we're connecting the intermediate and the distant or radiation zone for that. And so we end up with this as our total cross section. But then we need to solve the equation for the internal region, which is where neither of these are equal to 0, and then match it to those exterior solutions. So that is the exterior solution that we were doing above, so exterior to the potential. But as I sort of mentioned in the previous video, we still have the incoming wave here as being in the Cartesian coordinates, where for everything else we were using spherical coordinates. So to get this into the spherical coordinates, we can use Rayleigh's formula. And so we just have our e to the ikz being equal to this right here, where once again we have our associated Legendre polynomials and then our spherical Bessel functions here. So we can substitute this into the intermediate region equation from above, and so we put that in, we do some simplifying, and we end up with this right here. But then, because, we haven't really defined a potential here, it's going to depend on what we define our potential as, what this solution will actually end up being. And so we can look at an example here. So if we define a potential like this, so it's just a hard sphere of radius r equals a, so it's infinite potential inside the potential and 0 outside of it. We then end up with this right here. So our wave function will be equal to 0 inside the potential for all of theta, so for any angle around it. But our 2L plus 1 times this I to the L power is not equal to 0, and our Legendre polynomials are not 0, so that means that this, what I have here in brown inside these brackets, has to be equal to 0. So we end up with this, we do some rearranging, and we have our A sub L here, which is our partial wave amplitude. So we get this I out of the denominator here. Then the I can be pulled out in this equation here. So we just take this I and this I, we multiply them together, and we get this. And so we end up with this as our total cross section here. So we have our total cross section right here. And so we end up with this, with the 4 pi here from integrating over the phi for this. And we end up with this right here. So if we look at when the Ka is much less than 1, so that just means that it's a wavelength that's larger than the sphere, which is a low energy particle, then this Neumann function here will be much larger than this J sub L right here. And so we can just sort of cross that off right there and end up with this right here. We put that in here and end up getting this. And so we put that into our total cross section. We end up with this right here. But we look at this, and so when our Ka is much less than 1, then the higher powers of this, because we're raising it to, I mean, even if L is equal to 0, we're raising it to the second power. So those higher powers are going to be negligible. So the scattering is going to be mostly from this L equals 0 term. And so we put 0 in for all these L's on here, and what we end up with is this, which is on the order of 4 pi a squared, where a, remember, was the radius of our potential. So it's 4 pi r squared, which is the formula for the surface area of a sphere. And so what's interesting about that is it means that the particle is not just scattering off the face of the sphere pointing in the direction of the incident particle, but is scattering off the entire sphere. So remember, we're thinking of, I can draw a little bit better than that. So we're thinking of a sphere that looks like this. That's our potential, and so we're sort of shooting particles at it this way. And so you would think that, we could cut this in half, and only the parts sort of facing where we are firing our particles from is actually going to affect, how they bounce off of this thing and, which way they scatter. But what we find is that the sort of total scattering surface here is equal to the entire surface of this sphere. And so the back of the sphere is actually has to be included in our considerations for how the scattering is going to occur. But anyway, that was it for this video. So like I said, what we did was we sort of combined the outgoing wave for the intermediate and the sort of external or radiation zone here, and we ended up getting this right here. So that was for the intermediate region. Then we combined it with our with this, which is what we would get for the external region. And so we ended up getting this right here, which had this summation as our scattering factor right there. And so that gives us the solution for the intermediate region and the external region. And then we said that the internal region is going to depend on what we define our potential to be. And so then we sort of looked at an example of the potential being something like this, where it's infinite within the potential and then 0 everywhere else. But like I said, in the next video, we're going to combine this right here, which is our partial wave amplitude, and we will show how that is related to a phase change. So a phase change that happens when scattering, and so that phase change is dependent on the L. So different values of L, different angular momenta, will scatter differently, and so that will end up being important for that. But anyway, that will be in the next video. I hope you found this one helpful, and I will see you in the next one.